Okay, so we are talking about the third stage of planetary evolution, and that stage is slow surface evolution. So it is the tectonic movement, the erosion, the weathering of planets. And we had talked about Venus and the fact that Venus um, was very warm and certainly had lots of magma, but it didn't have tectonic movement because the planet is so warm that the crust bends instead of breaking. And as such, there is only one crust and one plate on Venus. Now let's see about our next one for Mars and how tectonic movement factors into what's going on Mars. Now with Mars, there is some heat. There's a bit of a liquid iron core, and there was one early in Mars's development and its evolution, but there's not an iron core now. So let's look at it back 3.5 million years ago, or 3 million years ago. Oh, excuse me, 3 billion years ago. It seems to run together. But if you think about it, 3 billion years ago, Mars did have an iron core, a bit of one, and it maybe didn't differentiate enough. And I say that because the crust is a bit too dense on Mars, but we'll get into that in a second. So maybe that dense crust should have moved down into the core, and that would have helped sustain the core a bit better. Mars has less planetary mass than the other terrestrial planets like Venus and Earth. And so energy equals mass times speed of light squared, E equals mc squared. So it's not going to hang on to its energy and its molten rock in the mantle as well as Venus and Earth do. Mars, because it has less mass, has less radioactive decay. It's a bit farther from the sun, so it gets a little less heat from the sun. And it does have a thin atmosphere, a very thin atmosphere. If Earth's atmosphere is 100 millibars of pressure at sea level, then the Mars atmosphere is 6 millibars of pressure, but we'll get into that soon. So as a result of that, there is some magma, there is some huge volcano, there are some huge volcanoes on Mars. Mars has actually the largest volcano in the entire solar system, and it is huge. Imagine a volcano that's 435 miles wide at its diameter. It's amazing. And there are other volcanoes on Mars that are nearly as big. All of this said, when it comes to tectonics, Mars has no plates. So Venus has no plates because it's so hot. Mars has no plates for another reason. Mars has no plates, and there's no evidence of plates on here that we can see. And we'll get into that evidence next, and then we'll go into why Mars doesn't have plates. Evidence of plate tectonics is basically lines on a map. Lines on a map that go a long distance. And those lines on a map are looking at plates that are either pulling away from each other or pushing up against each other or sliding each way past each other. These are long lines. And what we see on Mars are shorter lines that kind of look like a gravitational flow of lava. And there was some water on Mars, maybe gravitational flow of water. We'll get into the water later. But Mars isn't showing any evidence of plate tectonics. When I say lines and long lines, here's what I mean. Compared to the Earth, long lines around the Pacific Rim plate, long lines. and long lines down the mid-ocean rifts in the Atlantic Ocean. Long lines along the rural mountains between Asia and Europe. So this is what I'm talking about for long lines. We're not seeing that on Mars. We're not seeing tectonic plates on Mars. We're not seeing tectonic plates on Venus. The reason why we're not seeing tectonic plates on Mars and we're not seeing those long lines, the crust is just too dense. It can't break because it's so dense. That's why I said before that if Mars had differentiated in the first stage really well and all of its dense material moved down into its core, we might be talking life on Mars. It is a really pivotal step that Mars did not differentiate well in the first evolutionary period that we're talking about. Remember, first there's differentiation, then there's bombardment, then there's smooth surface evolution. We're in the smooth surface evolution now. Now, the crust was too dense to break into plates that could move, and those plates would move and erase the craters as they move, just roll right over the craters or move them apart and leave basins. But we still do have these shield volcanoes on Mars. And in fact, the north is covered with lava. The south is still cratered. So let's look into what these shield volcanoes are about if they are not about plates. So shield volcanoes are named that because they look like a low, broad shield that you'd hold out in front of you if you were a Roman, I don't know, a Roman knight or something like that, right? You'd hold a shield out in front of you and you'd want it to cover all of your body, so it would be a broad, shallow shield. That's why these are called shield volcanoes. They have lava flow that is highly fluid. So it really flows down a long way. And because it's so highly fluid, these eruptions go for decades. And in fact, that's what I wanted to get into about a bit about. You know, my favorite island is Hawaii and Mauna Kea. Well, on Hawaii, there is also Mauna Loa. And Mauna Loa is actually the highest volcano in the world if you consider its depth from the ocean floor. And Mauna Loa is an example of a shield volcano that we can look at on Earth, and we can also look at shield volcanoes on Mars. So Mauna Loa is not along the edge of a plate. Okay, here's the Pacific plate. This is the Juan Fuca plate. This is the edge of the Pacific plate. And Hawaii is 8,000 miles away from the edge. So when we talk about the Ring of Fire, we do not talk about Hawaii. Hawaii is different. Hawaii is formed from a hot spot under that plate. And Mars is all one plate. So some of the volcanoes on Mars form underneath the plate that has been weakened by the craters. And they can come up through the cracks in the plate with the magma, and this highly fluid lava can come out and go for a very long distance over decades and create a very giant volcano, the largest in our solar system on Mars. Now, it's kind of interesting. We know that Mars has a very dense crust because the crust on Earth that is in the area of Mauna Loa can't sustain Mauna Loa. And Mauna Loa is sinking into the ocean because the crust of the Earth cannot sustain it, while the crust on Mars is having no problem sustaining their largest volcanoes. The largest one is Olympus Mons. It dwarfs Mauna Loa at 435 miles in diameter. That's crazy. Mauna Loa is literally around 10 miles in diameter. Very different. The weight of Mauna Loa on the Earth's crust is producing a moat in the Pacific, which is growing year by millimeters, but it's growing, and quite a remarkable thing to look at. That's how we know that Mars has a very, very thick crust. And in addition to that, these are known for having I wanted to point out to you the long eruptions. Kilauea, which is another volcano on the island of Hawaii. You know, it's a chain, but these are all on the island of Hawaii. Kilauea has been erupting for 35 years. It just stopped in 2018. And in fact, you can't get property insurance on the island of Hawaii easily because the insurance companies are so worried that Kilauea will come back again. Kilauea shouldn't come back again. It should be done now, as it's been going for 35 years, but it's not extinct at all. Interesting stuff. Another shield volcano on Mars is well known. It's called the Tharsis Bulge in the Tharsis section in the north. You see these volcanoes. By all of these volcanoes in the north, we can know that this surface on the north is so smooth. It's got to be the youngest surface on Mars because it hasn't been cratered. And so we know that these volcanoes were at the end of the evolutionary period and they smoothed out Mars, but they were not associated with plate tectonics, which effectively smoothed out everything on Mars, if that makes sense to you. And I hope that, oh, got one more. When it comes to Earth, plate tectonics really changed the whole landscape of Earth, so we don't look like Mars. So for us, that slow surface evolution was like Goldilocks. We had lots of heat, but not too much heat. We had a liquid inner core, we had enough mass, we had radioactive decay, we were close to the sun, but not too close. We had a less dense atmosphere than Venus, but we had a lower density crust than Mars. And so as a result of that, on our Earth, our crust broke into plates. From one plate, it broke into approximately 11. So that's the difference there. And we're going to explore that more on the next video. See you then.